All right, let's get started. So today we're going to take ourselves a leisurely stroll through the Swift SDK, which got written actually after the Beam Summit last year, because there was the Rust SDK that kind of got started and didn't really go anywhere. And I was like, oh yeah, implementing an SDK be kind of fun. And then, what language to use. So Rust, obviously somebody already did. Also, I don't really like the Rust community. They're kind of, I know, but they got problems. They should fix them. Yeah, and then, like Swift is kind of interesting. It's in that same style of language. You get to keep a lot of the same features and do some stuff. And then, if I wanted to do one that was probably actually economically viable, C# would probably be a good choice. It has some nice features, and it's too Java-like, right? So it'd be kind of doing the same thing over again. So I decided to do Swift because that is the immediate question everybody asks when it's like, why did you write a Swift SDK? Isn't that for writing iOS apps? I'm like, yeah, but it's also, I just wanted to. And so that's why I did it. But it turns out that it's also a surprisingly good server-side language. Their Apple actually works on this, and the Swift community actually works on this. It's got good support across all the major operating systems, which was surprising. I was like, oh, it works on Linux, neat. It even works on Windows for reasons that are unclear. I guess maybe iTunes on Windows, who knows? It has a syntax that's actually, good for writing domain-specific languages to the extent that, Swift UI is a thing. That's an entire language, pure Swift, that doesn't have to play any compiler tricks. There's no XML or YAML or anything like that to get it all done. So that's kind of fun. It's compiled, but it still has some dynamic language features that it inherited from Objective-C. It actually has really good C compatibility for that reason. So memory layout is actually like Swift struct, C struct, same. They're both structs. They lay out the exact same way. So that makes like FFI type stuff really, really fast. Most of the time you don't even have to copy memory. And it's not garbage collected. It uses reference counting, ARC instead. So it's got pretty good memory profile. I mean, it is designed to run on relatively speaking, limited hardware compared to a laptop these days. Not that your phone is not powerful, but that's what it's designed to do. And also has surprisingly good protobuf and gRPC support. That's actually like developed and supported by Apple. I don't know why, but it does. And so that was really handy. So let's go take a look at what it looks like. So this, on the big screens, you can actually read it. So that's good. So this is a pipeline in the Swift SDK. And this is our friend word count. That's the batch version. But it's a fully featured word count. So in this case, it's a word count that is reading from GCS, from Google Cloud. And then it is converting those files into lines and then splitting those lines up into words and then counting those words. And then just for this particular example, I'm just having it log out to the console because I'm running it locally, but that's this .log. And this is what a pipeline looks like. And I don't know, I think it kind of works. It kind of got that pandas style to it, and is relatively easy for a user to understand and to extend. So let's go see how that works. We'll kind of start here and then work our way all the way back to the actual implementation of the gRPC stuff and like the data plane and the control plane and kind of pick it apart. So let's start. So the core element of the Swift SDK, so everything is represented using an enum, actually. So Swift enums are these pattern-matched enums like you see in Rust and other languages inspired by, I guess, Haskell is probably where this came from. Ken, you probably know better than me. ML? Yeah, close enough. Same difference. I'm going to get shot by the Haskell people now for claiming that ML and Haskell are the same. But anyway, and so the pipeline transform is kind of the core element. So everything you're looking at on that previous screen under the hood is building a graph using these enums. So, the core one here is, of course, Pardue, and this is the input collection, the optional name, the function to actually apply, right, in the Pardue, and then the output collection. So that's basically how everything is represented. And then, we have the specialized ones that Beam defines as other use cases in the enum. The most important ones here being probably impulse and group by key in regular usage, but also flatten and custom composite. So, basically the whole SDK is devoted to converting things into this. And then from this, we convert things to the pipeline proto and or construct the binary that we need to run a worker. And to do that, we use apply, just like you do in Java. So apply, even though you didn't see it in user code, and you would almost never use it in user code, apply still exists. It just happens to be something that is used primarily internally to construct this. So it's defined on P collections, just like it is in Java. And mostly what it does is it appends the transform that you specify, so the pipeline transform from the previous page, to the outputs of that P collection for the consumers of the P collection. So this is what's building up your graph, right? And so, for example, to implement impulse, we apply the dot impulse. So this is when you have, this is kind of a nice Swift feature. When you have a Swift enum and it knows which enum, you don't have to specify the enum name. You can just do dot and then the case. So that leads, it's kind of a nice feature, makes writing certain kinds of DSLs really easy because you can limit the language by just defining everything as an enum and then everything becomes dot. The protobuf library actually uses this extensively as well, because it also works on static functions and things like that. So here we define an impulse where our input is ourselves. The any P collection thing is just a type erasure mechanism, because the P collections are typed, right? They take a generic, but we want to be able to just hold anything. You need to wrap them up in this any to maintain the knowing what type they are, right? So by wrapping this up, we can extract the type name, do some reflection and keep it, and then recover it later. So it's kind of like a fairly common pattern in Swift, but it looks a little weird to the Java eye. But it's kind of like the type, it kind of serves the same role as type descriptor in Java implementations. And then we just set the output to output and return it, where the output is just an empty data collection, bounded in this case, right? Because the impulse is only ever going to send one thing. The other neat thing you can do in Swift is you can pattern match. So this is what's called an extension, which is kind of like, basically classes are extendable in Swift unless you work hard to make them not extendable. So as long, you can't change the memory layout, obviously, right? So you can't add new variables, but any function you want to add, you can just add it whenever you feel like it, which is, also makes doing that pandas style interface very easy because you can just add things directly to P collection instead of having to do some sort of visitor pattern-esque thing. But the cooler thing you can do, so that's pretty common, C# can do that too. Java could do it if it felt like it. But the cool thing that Swift does is, again, probably coming from ML or Haskell, is it lets you actually pattern match on the types that the collection takes. So P collection is always a P collection of, and I can make it so that impulse only exists on P collections of type never. So I can actually specialize where this function exists to the type of P collection that it is. So impulse can only be applied to never, which is always the root. So P collection nevers are root P collection that they do not exist in the graph, hence never. And so we can say impulse is there. We use this pretty extensively. Things like group by key. Group by key must operate on a key value. So it's only available on things that are key valued. And that becomes a compile time restriction, right? So when you're writing code, it actually helps debug a little bit because your code just won't compile if you're trying to do an operation on somebody needs a key value pair, for example. So that's really all there is to it. Surprisingly simple, right? And we can continue on this way to do more complicated things. So here's an example where this is just another way of specifying the type restrictions. So we're saying, okay, this must be a key value pair of string. So it's not just any key value pair, it's a specific key value pair. We want to be able to treat those as files to read or files to list for a file IO implementation. So we just do this, where we can read files and then we take a type of our source. So this is going to be a class rather than an instance, right? So it's going to be a class level object is that type, and this only exists on key value pair strings. And then on the protocol side, for file sources that you want to implement, we actually can define a protocol. Protocol is basically equivalent to interfaces, but they can define both instance and static methods, which I don't think interfaces can do, unless they've changed that. So that's actually kind of handy because you can actually put you can define static interfaces on things. Like, for example, here, where we say like, oh, if you're implementing a source, you should implement read files and list files statically so that we know how to convert these KV strings into data output, right? And then up here, I can just say, okay, yeah, so here's my source. So there's my source type. This is something in Java I cannot do, right? I can pass in this generic, I have this being, okay, it just has to conform to this protocol. You pass in the type here, and since I know it conforms to the protocol, I can call this static method on it without having to know what it is. And the compiler figures that out. And so that's actually where, like this little part right here came from, right? So I have a Google I/O, Google Storage file I/O source implementation, and I just say, okay, use that class, and it will resolve all that, do all the compile time stuff. So everything's still happening compile time here. There's almost no, there is, in the current implementation, we'll probably, like, to do like some of the more sophisticated like state and timer stuff, we'll probably need to, but there's zero reflection in the Swift SDK right now. It does it all compile time, which, you know, is more about the Swift language than it is about, like, that's not me being clever. I just copy patterns from other places. But, you know, so this is kind of how we build things up. So there are some gotchas, though, that don't exist in Java and Python. The first one is you can't actually serialize a Lambda or do a serialized function like you can do in Java. Like you can't, you know, slam some bytes together, throw it up on the wire. So we have to cheat a little bit in Swift. So the pattern we use is similar to the Go SDK, where I believe with the Go SDK, you have to register your functions with a name, correct? Revo? In the Go SDK, right, you register your functions with a name so you can call them later. I didn't want to do that. Like, that would have been an option, but it seemed kind of irritating. But so in Swift, what we do is actually, so Swift actually has some macros. And we wrote this, or I wrote this pretty early in the macro journey for Swift. So Swift macros these days are actually far more complicated. You can do some more interesting things. But at the time, macros were pretty limited. But two of the macros you have are something called file ID and line number. So file ID and line number actually uniquely identify a closure by where it is in the source code when you compile it. And because Swift binaries are always compiled from source every single time, much like Google 3 actually, you know, we can always uniquely identify it in a given binary. And that's actually what we use to register all of the closure names. And closures can be passed around like variables, which I think is a problem in Rust, if I remember correctly, where you can't really pass closures around. But here we can actually grab the closure as a variable called an escaping function, and then put it basically in a map so we can find it later when it comes time to do the process bundle. It also is the default name for things, which makes debugging a little bit easier because you're like, oh yeah, it's in that file on that line. That's where my problem is. And then, you know, the other thing that we ran into was our equivalent of Pardue is called pstream. So the element-wise Pardue is actually built on streams rather than the other way around. Stream is kind of the native Swift interface, really, is the asynchronous stream. So everything is actually stream-based, and then if you want an element-wise version, it's built on top of that. And the parameter packing stuff wasn't quite as developed as we had hoped when we did this. So, you know, we had to kind of hand implement each P stream we want, much like some of the other languages where you have just like, okay, this is the 3 output version, the 4 output version, the 5 output version. And you can, you know, this is again a common Swift pattern. So we had to go do that. In Swift 6, which should be coming out in a couple of weeks here, we can actually get rid of that because you now iterate over parameter packs and actually build that out dynamically. So that will actually significantly improve the code. But for right now, it's kind of a gnarly code. I didn't want to throw it up because it's kind of boring to look at, but that was the other kind of gotcha that we ran into. But it's also a very common technique. Swift UI does something very similar. So Apple and other Swift developers are highly motivated to make it more easy over time. So they're doing that for us. Yeah, so let's talk about pstream, right? So like I said, I just want to make sure we get through everything because I think there's 30 or so slides. Like I said, everything is kind of built on streams rather than element-wise. So that core stream we call pstream. So this is a function on P collection. So this is, if you're doing a very low level, you know, do-fun implementation essentially, or Pardue implementation, this is what you would use to do it. So most of the things that you use at a higher level are built on this or some variant of it. And so here, you know, it takes in potentially parameters. So this we can serialize. So these are all what are called codables. So codable is the Swift equivalent of serializable in Java. We also, specifically for Beam, because I couldn't pass up the pun, we have beamables. which are things that we know about a Beam encoder for. So, most of the primitive things like int and double and things like that, because you can add new functions to them, we're able to add the coder lookup directly to the primitive type. And now you can just ask for a type's coder if it's beamable. And so you can do that for any type you like. And it's a good name. It's fun. Beamable. It's a beamable item. And then in this particular case is a single output. So this is O0 is our other parameter type. So you can see that here. So, if there were two outputs, there'd be an O0 and O1, and everywhere you see an O0, there would be an O1 added onto that. You just kind of repeat that pattern over and over again. And then, of course, P collections, we don't have to specify it every time, but P collections are defined to be of something. So you always have access to the of, that is the input P collections type. And then, so here we just go through output, we create an output P collection of type. The resolve here is actually resolving whether or not the P collection is bounded or unbounded. So that's more of a convenience function. Anything else you'll see here up at the type, there's stream types unspecified. So if you don't specifically specify it, we'll try to resolve whether or not it's bounded or unbounded from the incoming type, from the incoming P collection. But if you run into a situation, where you're like merging two and one's bounded and one's not, right? You can always explicitly say, oh, there's a stream output, there's a bounded output, or this is an unbounded output. And you do that pretty rarely, but it's still there. And then here we're applying the Pardue. Parameterized closure fun is exactly what it sounds like. It holds a closure that you specify, and then it takes a parameter. And in this case, we could have done multiple parameters. I decided to make that a parameter object, so it doesn't get ridiculous. And then off we go. So for example, implementing reduce, with pstream, we have, in this case, the result, which has to be codable. So it has to be something we can serialize over the wire because we're going to want to be able to send it. We didn't require it to be beamable. So not all codables are beamable, but all beamables are codable. And then key value, because you're reducing over a key value. And you can also see here's another variant of the pattern matching. So you can pattern match up here on the extension, but you can also pattern match on a specific implementation. So, where of is a k value of kv, where kv can be any type. So here we're actually doing something, pattern matching wise fairly sophisticated, right? Like you can specify any key and any value type that you want. And as long as the input matches that type, it's not string or something like that, it will generate the correct compiled code for doing that. And then down here is our P stream. So here's actually where all the magic happens. So this right here is the important line. So these are, P collections are all modeled as Swift's asynchronous stream type, which is iterable. So you can say for a wait, which is, do an asynchronous wait, read in the value. So in this case, I called it KV, key value pair. So this is actually a tuple of the value, the timestamp, and the window coming across. And they all come across as a tuple. If you wanted to ignore these two, you just use underscores to ignore timestamp and window if you didn't want to use them for anything or something like that. And then you bring that off of the input, which is passed into the closure. So here are the closure arguments here. So this is the initial value, so that's the parameter that's coming across, the input P collection stream, and the output P collection stream. So by the time they get here, they're actually streams, they're no longer P collections. P collections are the graph construction mechanism, and P collection stream, which you get by calling .stream on the P collection, is the actual, I'm doing stuff now. So P stream actually does this for you, so you don't, generally speaking, have to worry about it. So you can see here, P collection .stream, P collection .stream. And here's actually the definition of the sendable, which has to do with the asynchronous, with Swift's internal asynchronous stuff. Sendable means it's kind of asynchronous by default. So you don't have to, it basically just keeps you from having to write a wait and a sync a lot. And then escaping means that you can capture parameters and things like that. And then because it's at the end of the function definition, Swift lets you do this thing where you actually put its definition not as a parameter to the class. It hangs off the outside as little braces right here. So that's actually a fairly common DSL feature. So a lot of things you'll see are these grouping. They look like groupings, but they're actually capturing closures and then lazily evaluated later. We actually use that for the pipeline itself. and then off you go. And then, we can build even more complicated things on top of that. So here's sum, which is just a simple implementation of a reducer over KV, where the value is required to be numeric, right? So yeah, so building up like higher level things is actually pretty fun and easy. And if you want to look at something a little bit more complicated, here's the file IO implementation. So that one is taking matching. So that's the P collection you passed in. And then here's your P stream, bounded collection in this case, because I happen to know it's file IO. Files are naturally bounded, so it must be bounded. But this is an area where I wanted to explicitly specify. And then the input is matching. So that's just the input P collection. So that's always going to be this guy here. And then output is where it's going. And then, guard is like it's a try catch clause, like a fast way of doing that. So it just basically makes sure that this actually works. If not, it throws. And then other than that, we try to connect to GCS and get ourselves some files. And we can emit as many times as we like with the .emit down here. It's a little hard to read. But yeah, so like, that's just kind of all there is to it. So everything you build everything out of P streams, and you can build on top of that. We do the same thing at the pipeline level. So, in this case, we have pipeline context, which is a class. And when you initialize, so this is like a little bit of syntactic sugar. When you have a constructor for a class, actually this is a struct, not a class, but that's a different. Structs and classes are pretty much the same thing. The difference between a struct and a class is structs are passed by value and classes are passed by reference. That's it. But if you have a constructor that doesn't have anything except a closure that it takes in, you can elide the bracelet, the parentheses, and just treat it like a grouping statement. So that's actually another kind of nice feature. Although here what we're actually doing is we're defining property on the pipeline class. And so the get is actually what's doing all the work here. Sorry about that. But so here to actually construct our graph, now we're actually getting to we're getting ready to send something onto the worker, onto the runner, so we can do some work. So we need to build the graph. So to do that, what we do is we get the root, which is just a never P collection. So it will not be represented in the graph, just serves as a central location to get everything. And then previously, when we constructed the pipeline, we captured the closure that defines the pipeline as a variable called content. And here we just run it with the root. So the little ampersand lets it be an in-out parameter. So that just basically lets the parameter be mutable. So now we can add things to the P collection. If we hadn't done that, you could add things to it, but they would only be local. And then the P collection itself, the root P collection would never be mutated, and you would get an empty graph coming back out. So this is just a little Swift in-out syntax. C# has the same thing. And then, we just basically do a breadth first walk over the transforms to pull out all the transforms, all the P collections, and then, essentially just go through and build the protobuf representation of each of those. So that's all that's really happening here. This is not particularly interesting. It's just, how to use protobuf with Swift. Mostly you do it with these .with. So .with is the protobuf builder in Swift. So what it's doing here is you're passing in a closure. That closure gets a single parameter, which is the builder object for the protobuf you're trying to build. You can give it a name if you want. I usually don't, but it's .0 if you don't give it a name otherwise. And so you can now go and set different parameters. And the cool thing is, for example, on spec here, because it knows the type of spec, it knows which .width to use. You never have to actually write down the name of the protobuf that you're actually trying to use. You almost never have to do that. So whoever wrote that on the protobuf team, well done. And then, we use all that to build out our pipeline context. So the pipeline context contains, of course, the pipeline proto, because that's the thing we're going to send to the runner. But it also contains all of the collections and all of the serialized closures for each of the Pardue. So as we're going through and we find a Pardue, we extract its name, and then the serialized function, because that's what's actually going to let us get from a pipeline proto back to bundle processing. Just keep an eye on time. And now we get to the, so now, okay, let's pretend we sent the proto off to the runner. In this case, say Prism, which we verified actually does work last night on the most recent version of both of these things, so yay. And it's actually really nice. Well, I'll do a quick demo. Like you can, like somebody asked, like, why would I use Prism? It's because it's really fast and runs inside my unit test, and that like makes testing so much easier than doing pretty much anything else once we get metrics working. But yeah, so we've sent it off to the runner. The runner's like relaunched the worker, and now we've got our binary, we've got our pipeline context because we launched the worker with the pipeline context that's just in the startup. What the worker do? And honestly, the worker was pretty easy to implement. I will say this, like, you don't have to do a whole lot to get your worker, to get your SDK up and running versus, what you might think when you first look at it. You look at it, you're like, oh, there's a lot of stuff to implement, but you really only have to implement one thing to get things up and running, and then you can start to incrementally add stuff from there. So in this case, this is just us setting up the gRPC connection. Again, like everything else, it too uses async stream, which is actually nice from an implementation perspective because everything's just an async stream all the way through, all running as independent tasks, and it's pretty easy to follow. And then here, we just spin off a task to anytime we get an output on the control plane to send that back to gRPC. So the async stream right here, it's backwards from what you'd almost expect, but to read things from an async stream, you use this variable here. And to write things to the async stream, use that variable there, is basically how it works. So we use that pretty much everywhere. And this is like the core loop right here. This is it. This is copy and pasted from the worker. There's nothing nothing removed from this particular piece of code. Like this is the only piece of the loop that you need. So we just wait for instructions from the control stream. It's backwards in gRPC for some reason. I think it's because control messages start coming without you actually making a request in Beam, which is a little weird. But yeah, you just immediately start reading from the response stream. You get your instruction request, and then one-ofs in protobuf in Swift are done as enums. So now you can just pattern match on the one-ofs. And so here's process bundle. So this is process bundle. And it takes the actual process bundle request. So the lets us extract it as a variable. And now we just find the processor that we need. We do some metric stuff. And then we spin off a background task. So tasks are just lightweight threads. They're pretty cheap. You don't really have to worry about them too much. They're managed for you. You can do more complicated managing things, like you can group them and stuff like that. But generally speaking, you can just spin them off, not worry about it. You don't need executor factories or anything like that. And then we just await processing. And that's it. That's the SDK right there, all done. We can go home now. There's obviously more to it than that because you got bundle progress and things like that. But that's actually, once you get this working, you can actually you can actually execute a pipeline in its entirety. And so, okay. Great. Well, how do we, but we have to actually know how to build out bundles and actually execute them. This is where the context comes back into play. So here is where we build out the bundle processor. So we get the instructions in, and then we basically go through, find all, for this particular transform, all of the inputs and the outputs, and get all of their streams. Streams are cheap, so there's no real cost in setting them up if we don't use them. It's easy, just put them in a list, and we're good to go. So that's all we're doing here. And you can see here, we're calling any stream, which is just the type erased version of the stream. So we don't have to worry about, because now we're in runtime and we don't need to do, we don't care about the type anymore, right? The type will resolve itself when it actually gets to execution. So for the purposes of holding it here, we just want the type erased. And then for the transforms, we just go basically arrange them into an array of steps that will all be converted into tests in a second. So we just go through, figure out what our inputs and outputs are from getting them from our input output list. And then we just, in this case, if it's a Pardue, we go and we append a Pardue step with the inputs and outputs to the list of tasks. For sources and sinks, Not the source and sink in your pipeline, the bundle processing source and sink, we have to do a little bit more work to attach ourselves to the data plane. So we handle those separately, but it's the exact same. They too are a step, so they're not special. They just aren't user accessible, right? And then once we're done with that, we could have done this all in one go, but I wanted to build everything up first and then launch all the tasks so I could group them together. We just, for every single one of them, because they're attached to each other by streams, which are all asynchronous, we just launch each of them as a separate task, which is, just a concurrency thing. It's not quite it's more like a green thread than anything else. So it will run some number of background threads, but it is lighter weight than a true thread. So it's not like a Java thread. And then off we go. We just wait for them to finish. And that's it. So that's bundle processing. It's like 10 lines of code. It's great. And then once it's done, we go in and return the results back to the responder, and that'll get routed through everything. So we don't actually even have to know where the control plane is. We can just write, as long as we have the responder, which is the other end of that asynchronous stream that's pumping things back to gRPC. We just have to know where it is, and we can just yield a statement to it. This one's a little bit more complicated because we also want to bundle up some of the metric stuff to send back. But so we end up passing it in a closure, but you can do that. It's fine. And off we go. And so, now we got to hook it up to the data plane. So, in SDKs, you got your control plane. We went through that, but there's also this multiplexing, demultiplexing data plane on the side where all of the actual elements come from. And so we do that with the source and sync step. So the source step, you can see here, is just bringing in a gRPC stream from the client. And then, this does some caching and stuff like that to reuse them and things. But generally speaking, it's creating another asynchronous stream specific to the instruction and transform that we're trying to process. So that's doing the demultiplexing. And then we just kind of pump them out onto the output. Off we go after we decode them and go on our way. So that's, very simple. And then the other thing we do is when we demultiplex things, there's an is last message on one of the elements that will indicate, that we're done with the stream and we can finish. We actually separate that out into a separate, data plane command, I guess, output command, to make it a little bit easier to write code against. So you can just, wait till .last, and when you're .last, you can finish. So calling output.finish will, in those, for await blah, blah, blah statements, calling .finish will now break out of that loop. So when we're done and we have .last, we can actually break all of those streams. So the user never has to think about that when they're implementing. They're just like, oh, the stream ended. They don't care why or how. And they don't care that they're going to be back in a second with the next bundle. They just think, oh, I've gotten all the data I could possibly get. So they don't have to think very hard about, how it's getting broken up and split and things like that. And then finally, what we do is we finalize the stream. That's talking back to the data plane to send the, yeah, we're done types of stuff. Syncs just do the exact same thing in reverse. So we pull things in and then push them back out onto the client stream. And you can see here we're using the ignore the input, only use the output kind of thing. We're running on time, so I'm moving a little faster. I knew 35 slides was going to be a problem. But yeah, so the data plane, we multiplex, demultiplex, relatively easy to do. So you can see here, we're just waiting. We bring them all in, and then I don't know if this is actually necessary, but I split the last element into its own thing and ensure that they always get called last. I don't know if that's necessary, but it seemed like a safe thing to do just in case. So that way it's always the last message on the thing so we don't lose anything. And, off we go. Multiplexing, same way. In this case, we're getting data in, we're getting timers in, and we're reconstructing them as data elements and then pushing out the data elements whenever we call the flush. There's also an explicit flush that you can flow through the streams, which are the streams themselves are not taking raw data. They're actually taking a typed enum. So you have, data types, last types, and flush types. And flush just lets us flush things, for example, when we're completing a bundle, or, we just want to do it every now and then for not performance reasons, like the opposite of performance, because it's probably slower, but for apparent progress reasons. And then, the only other thing that you have to do is coders. Again, enums, indirect enums just means you can refer to yourself. Right? Otherwise you can't, right? Otherwise you wouldn't be able to have a recursive enum. But in the case of coders, we need to be able to refer to coders, right? Because key values need to take coders or coders. And we use coders to construct beam values, which are basically just wrapping up the beam specific type. So, bytes or strings or integers and doubles and things like that. We can extract out the primitive type and put primitive types back in if they're beamable and that kind of thing. And there it is. Beamable is just define a coder as a property. So it looks like a variable, but it's not. It's dynamically constructed. But it's static. So you can also define static properties, which is kind of fun. And so in this case, now like data, which is a core Swift structure, right, that represents an array of bytes, has a .coder property on it that you can use on the .data class to always get its coder. It's kind of fun. So it makes implementing kind of the coder back and forth a little bit easier. Schemas, same story. I'm not going to spend a lot of time on this because we're one, almost out of time, and two, it's exactly like coders, but different enough that you can't reuse any of the code. That's one of the didn't go well kind of parts of Swift that we'll get to in a second. But let's wrap up and take some questions with what went well. So getting basic worker up, pretty easy. You only have to implement the one thing. That was actually really nice. The only gotcha I ran into is you have the custom metadata thing, which is not actually documented. But once you find it in somebody else's runner and you're like, oh, that's what that's for, everything's fine. And it's easy in gRPC, and gRPC kind of encourages that behavior. So I totally get why it happens that way. Lots of other APIs do it too. But it is surprising, like at the first, you spend the first like hour, like, why am I, and then you're like, oh, it's this custom metadata, done, cool. The data plane is pretty easy to implement, all that kind of stuff. Swift's asynchronous stream support, which was pretty new at the time I wrote this, made you saw a lot of that code's pretty small and pretty clean because it's all just like taking things off a stream, doing a thing, and then putting it back on the stream. And then Prism, these days, coming back to it after taking a little break, made doing some of the improvements more recently that I've been working on a lot faster and easier. What didn't go so well? The repository structure of Beam being the big monolith makes one thing kind of tedious that I wish weren't, and that's getting access to the protos. The FnApi protos, I think, are more generally, they're generally useful, right? As a, kind of almost HTTP for distributed processing. You even see it like Flink, for example, its PyFlink implementation uses FnApi to communicate between Java and Python. And to do that, they have to import all of Beam on the Python side, which causes some dependency issues, depending on how you're trying to package Flink. It'd be really cool if you could just get access to the protos, right, and use more bare gRPC to implement the FnApi more directly. Even with this, what we have to do is we have to manually generate from the protos into the Beam Swift, because the Swift Go and Rust uses kind of this pseudo monorepo type packaging style, right, where it vends all of the GitHub repos into the directory so it can build it. So it's building from source every time, but it does not know how to reach inside of a repo. And yeah, and then it won't let you go up because there's that's a bad security, but we don't want you reaching into slash. So you can't do that. So if it were separate, the package manager would have a much easier time. And I think other modern languages would also benefit from that. Prism is trying to solve this, but the runners are very inconsistent. The Python runner, the Flink runner have different levels of permissivity on what they'll let you do, but they're also just different. So some stuff will work on one, not the other. It's not clear why. And you're early on in the SDK development process can be very confusing. Like I say, Prism is helping with this, so this is less of a thing. And then the last thing is coders. Man, I wish schemas were something else, because they're not quite they're not the same as the rest of as the native coders. So you can't reuse any of the code, but you're doing the exact same code and you're replicating code that lots of other packages do these days. I know there are reasons, but it is super tedious to get it all completed. So getting complete schema support is pretty painful.